Okay, so let's start with question number 17. Question number 17 is on your screen. So the question number 17 says the number of phi zero subgroups in the symmetric group S phi of degree phi is. So basically what we have to find is the number of phi zero subgroups in the symmetric group S phi. So we know what is the symmetric group S phi, and then consider what you know what is the order of the symmetric group S phi. It is 5 factorial, which is 5 times 24. I write it. Okay. So we'll use the Silo theorems here. The third Silo theorem in particular. The third Silo theorem says that in any group, the number of p Silo subgroups will be of this form. Will be of the form 1 plus pk, which will divide order of the group, right? I mean, for different values of p. These are all possibilities. This theorem doesn't straight away say that these many subgroups will be there, but these are the only possibilities. This is what this theorem says. So in our case, the possibility are 1 plus the possibility of the number of the p Silo subgroup, phi Silo subgroup will be 1 plus phi k, which divides phi into 24. And by seeing this is of type 1 plus phi k, this will implies that the 1 plus phi k will divide 24. So we just have to look at the divisors of 24 which are of this type. Okay. So manually putting the values of k, where k, what is k? K is just 0, 1, 2, natural number with 0. So for k equals 0, it is 1. For k equals 1, it is 6. Yeah, 6 divides 24. Then k equals to 11 doesn't divide 24. Then 16 doesn't divide. Then 21 doesn't divide, and no more. So these are the only two choices we have, right? Okay. So the another Silo theorem, the second Silo theorem. The second Silo theorem says that the p Silo subgroup is unique if and only if it is normal. Okay, so we have only two choices. Either the phi Silo subgroup will be unique, or there will be 6 phi Silo subgroups in S phi. Okay, so what we know about the Sn group, right? For every n not equal to 4 in particular, the only normal subgroups of Sn are in fact the singleton identity element, then An and Sn. So these are the only normal subgroups for every Sn n not equal to 4. And here our n is 5. So these are the only subgroups, normal subgroups, right? And a phi Silo subgroup here will be of order phi. Okay, so that can't be this, that can't be An, because a phi will be of order I guess 60 here, right? Order of a phi is in particular order of Sn divided by 2. So here it will be 5 times 24 by 2, which is 60. So that can be possible, and Sn is not. So phi Silo subgroup won't be normal in Sn, hence 1 is not the choice. So number of phi Silo subgroups are 6. Yeah. So this is our final answer to this question number 16. The number of phi Silo subgroups in the Sn will be 6. Okay. So let's move on to the next question. So question number 26. Okay. Question number 26 says we have to check for the statements P and Q whether these are correct or not. So we are given the ring A, the ring R is in particular I will write in general form. There are rings are of this type: A plus B root D, where A comma B belongs to integers and D is any square free number. And I want to tell some theory behind this kind of rings. So whenever we have to find the irreducible element or prime element in this kind of ring, there is a function defined which is called norm. The norm function which is from the ring R to non-negative integers. How is that defined? Norm of any element a plus b root d is defined as modulus value of a square minus d b square. So this is norm, and this has some properties. First property is norm of an element is 1 if and only if that element is unit. Second property which is useful is norm of product is equal to product of norm. So in particular we are using these two properties. There are other properties also, like if norm of x is prime, it implies that x is a prime element, but be careful to use that because this is not a converse. The converse is not true. Okay, if the norm is a prime number, then the element is prime, but if doesn't imply that for every prime element the norm must be prime. This is not true. Okay, so here the ring is given as square root of a plus b square root minus 17. A, b belongs to integers. So d is minus 17 here. So norm will be norm of a plus b root minus 17 will be simply a square plus 17b square, which will anyway be positive or non-negative, which implies a square plus 17b square. Okay, so we have to check for the element 2 plus root minus 17, if I am not wrong. 2 plus root minus 17. Okay. So any element is called as irreducible when whenever it is expressed as a product of two elements, then one of them must be unit. This is our definition for reducibility. So let's check. If suppose we can express this element 2 plus minus root 17 as a product of two elements x and y. Okay. So what can we imply is norm of this element 2 plus square root minus 17 will be equal to norm of x into norm of y. And what is this value? This is 4 plus 17, right? Which is equal to norm x into norm y, which implies 21 equal to norm x into norm y. So norm x and norm y are integer values. So what can be choices? Like 21 can be only break into two different ways. It is like only 1 into 21 or like 3 into 7 without taking the shuffling in order. So there are only two possibilities. Okay, so we'll see if the latter case is possible or not. Okay, if suppose this is possible, it implies there exists some x such that norm of x will be equal to 3. What does it imply? Where x belongs to ring, so x will be of this form, like a naught plus square root of minus 17 into b naught, some kind of this. And what will be its norm? Its norm will be a naught square plus 17 into b naught square. But there won't be any solution to this equation, because you see, whenever a naught, the smallest value will be like 1 when a naught is 1 and b naught is 0, and if you increase any further value, it will be more than 3. So there won't be any solution to this equation. So this case is not possible. There won't be any x. So we have only this possibility, which implies norm of an element x or y must be equal to 1. One of these elements must have norm 1, and we know that norm is 1 if and only if x is unit. So what we arrived is, whenever you write 2 plus square root of minus 17 as product of two elements, which implies x or y must be a unit. So that's it. That implies that 2 plus root minus 17 is indeed irreducible. That's good. Okay. So we got that the P statement is correct, which implies 2 plus root minus 17 is irreducible. So we have to check whether this is the prime element or not. Okay. What the definition of prime element says is, if the element divides the product of two elements, then it must divide one of the two elements. Okay. So let's see. Okay, what we know is 2 plus root minus 17 into 2 minus root minus 17. What is this? A square minus b square, which is minus plus 17, which is 21. Okay. So 2 plus root minus 17 in particular divides 21, right? We can observe here, which in turn equals to 3 into 7. So 2 plus root minus 17 divides the product of 3 and 7, and I claim that this 2 plus root minus 17 cannot divide either 3 nor 3 neither 7. Okay, I suggest you, I will show why it doesn't divide 3. I will motivate you to prove by yourself that this doesn't divide 7. Okay, so let's see. If 2 plus root minus 17 divides 3, what this implies, 3 will be equal to 2 plus root minus 17 into some element y which belongs to R. Okay, but after applying norm to both sides, what we will have is norm of 3 equal to 21, which is norm of this element, into norm of y, right? Or what is norm 3, which is 9. So there is no way, because norm of y is an integer, there is no integer such that 21 into that integer is y, right? This is not possible. So 2 plus root minus 17 cannot divide 3, and hence in the same way we can show that 2 plus root minus 17 cannot divide 7 also, but it divides the product of those two elements, which is 21. Hence I arrived at the result that 2 plus root minus 17 is not prime. Okay, so with this I think we have an answer to this question, which says that P is an irreducible element and this is a prime element. Okay, so this is not correct. This is not a prime element. So the answer to this question is P is true, Q is false. B. Fine. Okay, so let's move on to the next question. Question number 44. So question number 44 says, let G be a group of order 5 raised to 4 with center having 5 square elements and the number of conjugacy classes in G. Okay, so we have to find the number of conjugacy classes with the given help. Okay, so we'll use the class equation theorem here. Class equation. One theorem says that for any group G, finite group G, we can write order of the group as the summation of order of different classes in that group where A belongs to G. What is A? It is just a representative of a particular class, the distinct classes. We just add the orders of the distinct classes exist, and that sum up to the order of the group. This is what the theorem says. Okay, and in particular we know if A belongs to the center, I represent ZG by center, that what is class of A, which will be singleton A. That implies there are 25 classes already are there, which are consisting of each element in the center, because we know there are 5 square, 25 elements in the center. Okay, so just we have to find the order of the class of the elements which are not in the center. Okay, let's see. Okay, if A doesn't belongs to the center, then we know that ZG is a proper subgroup of normalizer of A, which is in turn a proper subgroup of the group G. This symbol is for subgroup. Okay, this is not usual real number less than symbol. This is a symbol for subgroup. But what does this implies? Order of ZG will divide order of normalizer of A, which in turn divide order of the group. So we know this is 5 square and this is 5 raised to 4. So there is only possible choice here is 5 cube. Okay, so implies for every element which are not in the center has normalizer of order 5 cube. And we know what is the order of class of A, which is equal to order of G upon order of normalizer of A, right? Which is equal to 5 raised to 4 upon 5 cube, which is equal to 5. So what we find is, for every element which is not in the center, it corresponds to a particular unique class of size 5, right? So every element not in center has not in the center belongs to the class of size 5. So the group, order of the group can be written as 1 plus 1 plus 1 plus up to 1. How many times? The 5 square times. Why? Because each element belongs to the center, right? Plus 5 plus 5 plus 5 plus, we don't know how many of these classes are there, so we just assume this to be 5 k, suppose. So what we have found is 5 raised to 4, which is equal to 5 square plus 5 times k, which implies 5 raised to 4 minus 5 square by 5 equals to k, which implies k equals to 125 minus 5, which is 120. Cool. So what we have found is there are 120 classes here and there are 25 classes here. So the total number of conjugacy classes is equal to 120 plus 25, which is equal to 145. That's it. Okay, so answer to this question is 125. Good. So let's move on to the next question. The question number 45. Okay, the question number 45 is on your screen. Let F be the finite field and F star be the group of all non-zero elements of F under multiplication. If F star has a subgroup of order 17, then the smallest possible order of the field F is. Okay. So knowledge we required is for every finite field F, order of the finite field F will be of this type, P power K, where P is a prime. P is prime. Okay, and K is any natural number. For every finite field, its order will be of this type only. This is the only case. And which implies then order of F star, which is the group of non-zero elements, will be what? P power K minus 1. What we know is it has a subgroup of order 17, and by Lagrange's theorem we know that order of a subgroup will divide order of the group. Okay, so this implies 17 will divide P power K minus 1, right? Okay. So the task now for us is to find a smallest possible value of K such that 17 K plus 1 is of this type, P power M, for any sum, suppose M belongs to natural number and P belongs to, and P is prime. Okay, the smallest possible value of K for which this equation holds will be our answer. Okay, so let's see what can happen. Okay, so suppose for K equals to 1, we have 17 plus 1, 18, which is not a prime power. Then 17 2s are 34 plus 1, which is 35, which is in fact not the prime power which we want. Okay, so next is 17 3s are 51 plus 1, 52 is itself not a prime power. Okay, now 17 4s are is 68 plus 1, which is 69. Is it a prime power? No, this has divided 3 times 21, which in turn has 3 into 7 into 3. So this is also not a single prime power. Then 17 times 5, which is 85. 85 plus 1, is it the prime power? It is 86, which is 2 times 2 4 8. Okay, so no, this is also not a power of single prime. Now 17 times 6. 17 times 6, okay, which will be 102 plus 1, which will be 103. So I guess, yeah, this is a prime number. If I am not wrong, yes, I think 103 is a prime number. So the 103 is the least prime such that 103 minus 1, 17 divides 103 minus 1. So we are done. So the answer to this question is 103. So that's all. I think you have understood the questions. So thank you for watching the video.